Mr. Corsey here. Now this is going to be a fairly long video, so I've made chapter headings, and what that allows you to do is to slide through your timeline on YouTube, and you'll be able to see where the particular questions are if you're hunting for one question. So let's get going. So here's question 1, where we're asked to expand and simplify this algebraic expression. We have two brackets. The first one has a linear expression, 3x minus 2 terms in that expression. The second bracket that we're multiplying is a quadratic expression, so there's 3 terms in that second bracket. Now, just to emphasize that, let's highlight these terms. There's the first term in the first bracket. There's the second term in the first bracket. And then in the second bracket, there's the first term. And there's the second term. And finally, there's the third term. Now you notice that when I'm circling these terms, the positive or negative sign is also included. Now, the idea here when we're multiplying out is we have to make sure that that red term, the 3x in the first bracket, multiplies each term in the second bracket. So we'll have red times the green, red times the blue, and red times the purple. And also we have to make sure that the yellow term, that's the negative 2, multiplies each term in the second bracket. So yellow times green, yellow times blue, yellow times purple. So altogether there'll be 6 products. 6 products. So let's get going with this. So red times green, there's 3x times 2x squared. That'll give us 6x cubed. Now if you're not sure about that, let's just illustrate that, see what's going on. There's your 3, there's a times x, there's a times 2, there's a times x squared, which is x times x. So 3 times 2 is 6, x times x is x cubed. So we've got 6x cubed. So red times blue, 3x times 5x, that'll be 15x squared. Red times purple, that's 3x times negative 1, that'll be negative 3x. Now that's us taking care of the 3x. We've now got to go to the yellow term, the negative 2, and make sure each term in the second bracket gets multiplied by negative 2. So we'll have negative 2 times 2x squared, that's negative 4x squared, that's yellow times green. Yellow times blue, negative 2 times the 5x is negative 10x. And then finally, yellow times purple, negative 2 times negative 1, that's positive 2. And finally, we need to match together all the like terms. Well, we'll look for x cubed. There's only one term involving x cubed, that's the first one. So it sits in splendid isolation. Now let's look for terms involving x squared. There's one of them and another one. There's 2 terms involving x squared, 15 of them minus 4 of them. That's 11 of them. It's 11x squared. Look for terms involving x. There's 2 of them, negative 3 and another negative 10. That's negative 13x. And then finally constants, just the 2 at the end. So there's plus 2. So that's our final result. It's a cubic expression, 6x cubed plus 11x squared minus 13x plus 2. But you'll notice in working out we had 1, 2, 3, 4, 5, 6 terms. Each term in the first bracket has to multiply each term in the second bracket. So here we have question 2. We have a company whose annual profit at the end of 2021 was 215,000, and they're expecting their profit to increase by 3% each year. all the way through to 2025, and we were asked to calculate their expected annual profit if that happens by the end of 2025, giving an answer correct to the nearest £1,000. So let's just have a wee look at what's going on. We're sitting with a profit at present, that's in 2021, of £215,000. And then we've got an increase. We're adding 3% to that to get to 2022. Another 3% increase to get to 2023. Another 3% increase to 2024. And that goes all the way up to 2025. So just one more. Add 3%, 2024. To 2025. So it would appear what we should do is we take this sum of money, work out 3% of it, add it on, we get a new sum of money. We work out 3% of that, add it on, get a new sum of money, and then continue all the way down to 2025. However, there is another way of doing this rather than working out individually and adding. 3% of this is 3/100ths. That's 0.03. And the whole lot, that's 100%. Now, really, if you're adding 3% to the whole lot, that's 103%. And remember, 103%. 103 divided by 100, which is 1.03. So this 1 tells you that it's the whole amount, and this 0.03 is your 3% increase. So we've got our 100% plus our 3%, and we've got this what's called a multiplication factor of 1.03. So when we start out with 215,000, and this time we multiply by 1.03, we'll be ending up with the correct sum of money for 2022. In other words, this is in effect the same as finding 3% and adding it on to the original. In one calculation, we take this sum of money and multiply it by 1.03. And then we take this sum of money and do the same. So we've got a whole load of multiplyings by 1.03 having the same effect as working out 3% and adding on. And how many are there? Well, there's 1, 2, 3, 4 of them. So the expected profit by 2025 would be our original sum of money, 215,000, multiplied by 1.03, and whatever we get for that, we'll then multiply by 1.03, whatever we get for that, that's in here, we'll multiply by another 1.03, and then there's finally another one to be multiplied by, and that gets us to 2025. So if we look at this, we've got our 215,000, and we've got 1, 2, 3, 4 1.03s multiplied together. Now in calculators, that's easy to do. We just take it to the power 4 of them multiplied together. So here's the sum of, or the calculation to get the sum of money profit by 2025. So let's launch into the calculator now just to see what goes on, and let's put in the sums. 215,000 times 1.03 raised to the power, on this calculator it's that, sometimes it's this wee hat symbol, raised to the power 4, that should give us our answer. And there it is, 241,984 pounds, and then there's a whole load of rubbish at the end. So how do we write this? That's approximately to the nearest 1,000. There's units, tens, hundreds, there's thousands. We're going to be chopping a 9 off, so that 1 goes up to 2 in the thousandths place. And of course, we need to indicate that that's thousands by putting all these zeros in. So it's 242,000 to the nearest £1,000. So we'll put that down to the nearest 1,000. And that's our expected profit for the company in the year 2025. So here we have question 3, where we have a concrete gate post. Consists of a sphere sitting on top of a cuboid. Various dimensions are given to us, and we're asked to work out the volume of concrete needed to make the gate post. So the strategy we're going to use, the volume of the gate post, that'll be given by adding the volume of the sphere to the volume of the cuboid. So sphere plus the cuboid. So that's the overall strategy. So let's work out the volume of the sphere first. So the volume of the sphere, and if you don't know the formula for the volume of a sphere, well, you're lucky, because at the beginning of your exam paper in the formula page, you're given the volume of a sphere. There it is. V equals 4/3 pi r cubed. Now, we are allowed to use calculators, so you do have a pi button available to you. Radius, well, if we look at this sphere, we're told the diameter, that's from one edge up to the other opposite edge. The radius will be from that edge to the centre, that's exactly half of the diameter. So that'll be 0.2 metres. So 0.2, and we have to cube that. So there's the calculation we have to do. Now, out of interest, metres, meters, meters, everything's in metres, so we have no unit conversion to consider. And our final answer will be in cubic metres, since they're volumes. So there's a calculation that we'll do. Let's have a look at the calculator, see if we can get going with that. So 4/3, 4, divided by 3, times your pi button, times 0.2. Now, raised to the power of, in this calculator, that's the key. Sometimes it's labelled with a wee hat. Other calculators have other ways of identifying it. But know your own calculator, know how to do that in your own calculator. So there's the calculation, and there's the final answer. Now, approximations will wait till the end. We know it's roughly 0.0335 and so on, and that's cubic metres. Rounding of answers will do at the end. So that's the volume of the sphere. Next, we'll tackle the volume of the cuboid. Now, if you don't know the volume of a cuboid, then tough luck. You won't get that at the beginning of your exam paper. It's length times breadth times height. So if you don't know that, learn it. So we need to look at the various dimensions. So length, quite clearly 0.48 times the breadth. Well, we don't have the breadth. However, we're told it's a square base, so it'll be the same as the length. So the breadth will be 0.48 also. Now watch out for the height. It would appear that the height's 2.4 metres. However, if you look closely at the diagram, you're told that the total height is 2.4, not the height of the cuboid. So we have to subtract this 0.4 width of the sphere, diameter of the sphere. We have to subtract that 0.4 from 2.4, and we'll get exactly 2 metres for the height of the cuboid. So there's our calculation. Let's bring on the calculator to perform that. So 0.48 times 0.48 times 2. And that gives us a grand total of 0.4608. And again, that's cubic meters. Now, our final answer then, total volume of the gatepost, that'll be the sum of these two numbers, the 0.0335 from the sphere plus the 0.4608 from the cuboid. And let's go to the calculator for that. There's that one plus that one. If you're wise, you'll have stored these in your calculator, and that gives us 0.4943 and so on. Now, approximations, I would take this to 3 significant figures. So it's approximately, now remember zeros at the front are not significant, they just indicate that that's the units column. But the 494 are significant. You're chopping a 3 off, the 4 remains as a 4, so there's no rounding up. So it's 0.494 cubic meters, and you've vandalised that number a bit, so declare what you've done. That's to 3 sig figs, 3 significant figures. And that's your final answer. So here we have question 4, part A. And we've got Moira, who's off to the fruit shop. She's buying mangoes and apples, 4 mangoes, 3 apples, spent £4.25. We're asked to write down an equation to illustrate that information. So the crucial thing here is to explain what the letters we're going to use stand for. So let's say a mango, costs, and so we don't get confused, let's just use the letter M for mango. So a mango costs £M, an apple costs, well, you've guessed it, £8. So what's the cost of 4 mangoes? Well, if one of them costs M, 4 times that would be 4M. So there's 4M, that's the cost, pounds, for these 4 mangoes, plus 3 apples. That's 3 times the cost of one of them. So that's 3A pounds for that. So the total cost when we add these up is £4.25. Now we don't need to put in the pound signs all the time, because these pure numbers will equal this number plus this number will equal this number. So there we have an equation, and it illustrates that information. Let's have a look at part B. Sammy is off to the same fruit shop, buying 5 mangoes and 2 apples, costing £4.70. We have to write down similar equation to illustrate this one. So the cost of 5 mangoes would be 5M, 5 times the cost of 1, 5M pounds, and the cost of 2 apples would be 2A. And that has a total cost of £4.74.7. So there we have an equation to illustrate that new information. Now, moving on to part C, asks us to calculate algebraically the cost of a mango and the cost of an apple. Now, you'll recognise this as being a system of simultaneous equations, and to solve these, we usually attempt to get the same number of M's or the same number of A's in this case. And I think let's concentrate on the A's. If we were to double everything in the first equation, we'd end up with a 6A there. If we were to treble everything in the second equation, we'd end up with a 6A there, and life would be more interesting, would it not? So part C, let's move on with this. So doubling everything in sight in the first equation, 8m plus 6a equals 2 4s are 8. 0.25 times 2 will be 0.5. Second equation, if we treble everything, 3 lots of 5m is 15m. 3 lots of 2a is 6a. And 3 lots of 4.7, 3 7s are 21, 3 4s are 12, plus the 2 is 14. So you can do this in your calculator if you're not sure of that. So 14.1. So there we go. Now, what can we do in simultaneous equations like this? Well, what we do is we try and get rid of the letter that we've made the same number. So we would subtract the second equation from the first equation. So 15m from 8m, well, I am just wondering here that we don't want negatives, so maybe we should subtract the first equation from the second one, and that'll avoid these negatives that we would get. So 8m taken away from 15m will be 7m. 6a away from 6a vanishes, that's why we did this times 2 and times 3. And then 8.5 away from 14.5 will give us 5.6. Again, do that in your calculator if you feel more confident with that. So we're almost there. 7 times m is 5.6. To get m, we'd divide both sides by 7. So 7 eighths are 56. So 7 into the 5, 0, and 7 into the 56 tenths, as they are, would be 8 tenths. So there's 0.8. Again, do that in your calculator. So calculate algebraically the cost of a mango and the cost of an apple. We've found the cost of a mango. So what we use now is one of these equations to find the cost of an apple. Let's use the first one. So we'll let this value which we've discovered, let m equals 0.8 in the first equation, and 4m plus 3a equals 4.25. So we do a wee substitution. So 4 times 0.8 plus 3a will give us 4.25. So calculating that out, 4 lots of 0.8, do that in your calculator if you want to, it's 3.2 plus 3a is 4.25. Now what do we do? Well, let's take 3.2 away from both sides, and the left side will be left with 3a, and 3.2 away from 4.25 will be 1.05. Divide both sides by 3, a equals 0.35. Now, we haven't actually found the cost yet. We've found the values of m and a, so let's just state what we've found. A mango costs 0.8 pounds. That's 0.80, 80 pence. An apple, well, apple costs 0.35 pounds. That's 35 pence. So algebraically we've found, because we've solved equations, algebraically we've found the cost of a mango, 80 pence, and an apple, 35 pence. So here we have question 5, school netball team, and they're doing sit-ups, 7 players, and they record the number of sit-ups they do in a minute, and that's where we've got these 7 numbers from. There's 7 data points in this statistics question. And we're asked to calculate the mean and the standard deviation for these 7 data points, or the 7 numbers that we've got. So let's first of all start with the mean. And in statistics, our notation for the mean is x bar. And it's the sum of all the data points. Now the sigma is a capital sigma, it's a Greek letter. Statistics, it's short for summing a whole load of things. And x stands for each of the data points. So it's the sum of all the data values. And we divide by the number of data points that we've got. In this case it's 7. So you can check this in your calculator. When we add all these numbers up, these 7 numbers, we get 182. And there are 7 of them. And again, check this, but divide by 7, you get 26. So the mean is 26. Now the standard deviation, we've got a symbol for that. It's S. And we have 2 versions of a formula for this. Both will give the same results. I'm going to be using the first one, and you can check in your formula sheet, but there it is, standard deviation S, and it's the square root of, we've got a sum of squared terms, and each term is the difference between a data point and its mean value. We'll see how that works out in a minute. And we divide that not by the number of data points, but one less than the number of data points. So that's the fairly complicated formula. Now, best I think to set out a table to do the calculations, or set out the calculations that we need for this. So the first column will involve x, each of the data points. So let's list them in the column. There's 29, 27, 24, 31, 22, 19 and 30. Now the first calculation we have to make is the difference between a data point and the mean, x minus x bar. So for instance, in this first row of the table, we've got data point 29, and we have to subtract the mean value of all the data points, which is 26, from it. So 29 minus 26 is 3. 27 minus 26 is 1. 24 minus 26, that's a negative number, it's negative 2. 31 minus 26 is 5. 22 minus 26 is negative 4. 19 minus 26 is negative 7, and finally 30 minus 26 is positive 4. Now the squared term is the square of each of these values, so we take this difference and square it. So we're going to get positive numbers in here. Square terms are always positive or 0. So 3 times 3 is 9, 1 times 1 is 1, negative 2 times negative 2 is 4, 5 times 5 is 25, negative 4 times negative 4 is 16, negative 7 times negative 7 is 49, 4 times 4 is 16. And what have we to do with these? We have to add them all up. So down here we'll find the sum of the squares of all these differences. So that's summing the numbers in this column. And we do get 120 if you check that. So 120. Now we've still to divide that by n minus 1. And take the square root. So there's 120 for the top of the fraction. N minus 1 is 7, number of data points minus 1, which is 6. So we've got the square root of 6 into 120 goes 20 times. So square root of 20, you can get the calculator out to do that. Square root of 20 and there it is. It's 4.472, and so it goes on. So approximately, let's round it to 1 decimal place, there's 4.5. And we'll just say what we've done when we've vandalised that number. It's the 1 decimal place. So that's our standard deviation. Let's now move on to part B. It says some players in the school hockey team also recorded number of sit-ups they completed in a minute, and their numbers gave us a mean of 29 and a standard deviation of 32. Now, to make two valid comments comparing the numbers of sit-ups of the players in the netball team and the hockey team, well, let's first of all look at the mean, the average value, mean. And in the netball team, that's the one we did first, I've got an average or a mean value of 26 compared to the hockey team, mean value of 29. So the statement we can make is, on average, the hockey team did more press-ups, or not sit-ups, they're not press-ups, sit-ups. An average hockey team, hockey did more sit-ups than the netball team. Now that was 29 mean compared to, what was the other one? 26 we calculated. So there's the two means compared. And because the hockey team had a higher mean than the netball team, that means their average number of sit-ups was more than the netball team. So that's the first statement we can make. That involves the mean. Let's look at the standard deviation. Now, standard deviation tells you how spread out the data points are around the mean. And if we compare the hockey team standard deviation of 3.2 with the one that we calculated, 4.5, you can see that the hockey team is less varied, less spread out, deviates less from their mean than the other team, the netball team. So the number of sit-ups performed by the hockey team was less spread out. That's around the mean. Less deviation than that for the netball team. So that would get us our marks. I mean, they're less varied, more consistent, spread out less. Any of these terms would do for that. So there we have it. That's the answer to question 5. So here's question 6. We're given the diagram of a triangle, various lengths, couple of sides, angle in between these two sides, and we're asked to find the area of that triangle. Now we do have a couple of formulae for working out the area of a triangle. The first one, half base times height. Unfortunately, we don't have a perpendicular height for this triangle, so that formula's out. There is another one that involves using trig. At the front of your exam paper, you'll find this formula. Area of a triangle is a half AB sine C. Now, that involves a triangle ABC. Remember, the side opposite angle A is little a, side opposite B is little b, and side opposite angle C is little c. So a half AB tells you to take a half of this side A times this side B and the sine of the angle in between them. So it involves two sides and the angle in between. That's exactly what we have here. So let's first label the sides. This is little g, its opposite angle G. This is little h, as its opposite angle H. And we've got the angle in between them. So the area of triangle FGH will be equal to a half. Now it's the two sides multiplied together, G times H, and the sine of the angle in between them. So there's the version of this formula that applies to this case. So let's just plug in values. A half of G is 32, H is 25, and sine of the angle F is 58 degrees. So at this stage we've now got a calculation to do. Let's bring out the calculator, put it over here so we can see it all. Now, since we're using a sine, you need to check that your calculator, in my case it says deg up here. Your display might have a D or a deg, but it certainly should not have GRD or RAD on it. It must have deg or D to show you're working in degrees, or you will get the wrong answer. So make sure your calculator's in the correct mode for working with degrees. So let's just plunge ahead with this. A half, that's 0.5 times 32 times 25 times, and then the sine of the angle 58 degrees. And that all comes to 339.219 and so on. Now, there's a problem about accuracy and units and so on. It doesn't say anything about that. We know the measurements of the lengths were centimetres, so this area must be in square centimetres, but how accurate should we make this? Well, probably 3 significant figures would do, so probably 339 to the nearest square centimetre. So we'll put that down to 3 sig figs, or to the nearest square centimetre. Sig figs being significant figures. So there is the final answer with our accuracy stated and the units, square centimetres. So here's number 7. We have a healthy looking quadratic equation to solve. Now, sometimes quadratic equations you need to try and factorise the quadratic expression. That's one of the ways of solving them. However, when this says give answers correct to 2 significant figures, it's a pretty good clue that this will not factorise, and you're being invited to use what's called the quadratic formula. Now, the quadratic formula you are given at the front of your exam paper in the formula sheet. It says the roots of ax squared plus bx plus c equals 0 are this expression here. And we have to compare this ax squared plus bx plus c equals 0 with the given equation to find out the values of a, b and c to plug into this hefty formula here. So that's the first thing that we'll do. So let's do that. We'll compare 4x squared plus 2x minus 7 equals 0 with the standard version, ax squared plus bx plus c equals 0. So now we know what a is. There's 4 lots of x squareds. That's what A stands for. Number of x's, B is 2. And the constant at the end, C, is -7. So these are the 3 values. So x, therefore, must be equal to, and let's just plunge away at this. So negative b, that will be a -2. We have a choice. We either add or we subtract. And we've got a big expression under the square root sign. It's b squared, that's 2 squared, minus 4 times a, which is 4, times c, which is -7. And then bottom of the fraction, 2 times a, and we know a is 4. So that's the calculation that we're doing. And there's bits we can do without a calculator just to tidy this up. So -2 we're adding or we're subtracting, there's a choice. Square root of, now 2 squared is 4. And let's work out -4 times 4 times -7. So that whole second part will be a positive value. 4 fours are 16, 7 16s. We need to work that out in a calculator, I suppose. That's worth doing. 4 times 7. Well, that comes to 112. There we go. So that's 112, and that's all over 8. So it's -2 plus or minus the square root of 116 over 8. So there are 2 values for x. X is either -2 plus the square root of 116 over 8, or x is equal to -2 minus the square root of 116 over 8. So we need to work out these values on the calculator. So let's work out this first one. So let's have a -2. So there's a -2. We're adding, and it's the square root of 116. And then once we've got that, so let's just work that out. That's that sum. Once we've got that sum, we'll take that answer and we divide it by 8. And there we get 1.096, and so on. Now the second choice, x could be, let's work this one out, -2, there's our -2, and this time we have to subtract the square root of 116. And we'll find out what that number is first, and then take that answer and divide it. See, it's the whole of that answer we have to divide by 8. So I'm being a bit wary about that. I'm working out the top of the fraction first before I divide by 8. So it's that answer divided by 8. And that gives me -1.596, and so on. So there's our 2 values for x, and let's just read the question again. It says give your answers correct to 2 significant figures. So x is approximately 1 point, and this 0, since we're chopping a 9 off, will round up to a 1. There's 2 significant figures for x, or x is approximately the second value, -1 point, and chopping this 9 off that 5 rounds down, if you like, to 6. So it's -1.6. So there's our 2 approximate values for the solutions to that quadratic equation. So here's question 8. We're shown a circular train tunnel which is sitting on a horizontal floor. And here's a diagram of the cross-section of it with various measurements put in, and we're ultimately asked to calculate the height of the tunnel. That's from the floor up to the tip of the ceiling of that tunnel. So let's look at a larger diagram, and because we're told that this chord, or this line AB, the floor of the tunnel, is a chord of the completed circle, it means we can look at the midpoint of that. Let's call that M. In other words, this distance is 2 meters. That midpoint M, if we drew a line perpendicular up to the top of the tunnel, let's call that N, at right angles, then it will pass through the centre of that circle, and we'll get the height that we're required being the length of this line MN. And a bonus is that we've now got a right angled triangle, and we've also got a radius up at the top here. So we know that the line ON is a radius, and that means that we immediately know the length of ON. It's 2.9 meters. Well, that's useful because it means we've now got to find OM. Add these two lengths together and we'll have the height of the tunnel. So let's look at that triangle AMO in more detail, because that's certainly the triangle that's going to help us on the way. So we know this length AM is 2 meters, and we know from A to the centre is a radius, which we're told is 2.9 meters. So in this triangle, we're looking at Pythagoras' theorem. Now, it's not the hypotenuse that we're going to be finding, it's one of the smaller sides. So to find OM squared, we'll take the square of the hypotenuse, that's OA, and subtract the square of the other smaller side. So it's not an addition, it's a subtraction because we're finding one of the smaller sides. Now OA squared, that's 2.9 squared. AM, that's 2 squared. And we can work this out. We need to get our calculator onto it. 2.9 squared, and we're subtracting 2 squared. And that comes to 4.41. So that means that OM is equal to, well, we undo that square by taking the square root. So we're looking for the square root of 4.41. So it's the square root of 4.41. That comes to 2.1 meters. So the height, well, let's get rid of this. The height of the tunnel, that's just the length of OM plus the length of ON. So that's our 2.1 plus that radius length of 2.9, that comes to 5 meters. So that's the height of the tunnel, 5 meters. So here we are at question 9, where we have to solve this trig equation, 3 lots of sine x plus 4 equals 6, and we have to solve it for angles ranging from 0 degrees up to 360 degrees. Now, what we could do to begin with is let's compare a simpler equation where instead of sine x we've got x, and if we were given this to solve, we'd do the usual, we'd subtract 4 from both sides, and then we'd divide both sides by 3, and we'd end up with our solution. So at least if we did something like that, we would have made some slight progress. So let's do that. So we've got 3 lots of sine x plus 4 equals 6. we'll take away 4 from both sides. So we'll get 3 sine x equals 4 from 6 is 2. And we'll divide both sides by 3, as we did in the simpler equation above. And we're ending up with sine of x equals 2/3. Now what do we do now? Well, we're looking for an angle whose sine is 2/3. And this really involves calculator work. Now make sure please that your calculator is in the correct mode. It should have deg, not GRD or not rad. It should be in degree mode so that it recognises that we're using degrees as the angle measurement. So sine of an angle is 2/3. This button here, sometimes it's sine to the -1 on your calculator, would involve finding the angle whose sine is 2/3. This button is the sine of a given angle, but we're trying to find the angle, so we would use this button, the angle whose sine is, or sine to the -1 is another indicator of the correct key. So the angle whose sine is 2/3, and we get this 41.8. And that's to 3 or to 1 decimal place. Now, that would be the end of the story, however it's not. Let's have a look now at a typical sine curve. And what this does is shows us the value of the sine on the y-axis for various angles. When we go from 0 to 90, the values of the sine go from 0 up to 1. There's 1. And from angles that go beyond 90, from 90 to 180, they're called second quadrant angles. It's a very symmetrical graph. The values then come down from 1 down to 0. And so it goes on. From 180 to 270, what's called third quadrant angles, the values of sine become negative, and they go down to a minimum value of -1 for the sine of 270. And then for angles between 270 and 360, the values start increasing again back up to 0. So the sine of 360 would be 0. Now what we're asked to solve in this equation is to find angles whose sine is 2/3. Now on this diagram, 2/3 will be about there, and therefore we're looking for heights in this graph, values of sine which are 2/3. So there's the 2/3 value, and we can see that yes, there is an angle that gives us that height of 2/3, and that was the 41.8. Let's just round it to 42 degrees. There's 42 degrees. Sine of 42 degrees is approximately 2/3. But look at this. There is another angle, what's called a second quadrant angle, which has a sine that's 2/3. Now by the symmetry of this, if we've travelled from 0 to 42 degrees, then travelling from 180, the same distance along this angle axis, back the way, we would end up at the required angle. So we have to take 180 and subtract this angle, 180 minus the 42, to get the angle we're after. So what we now have to do is to say this is in the first quadrant, That's the normal first quadrant angle. And we say for second quadrant angle, and we know that there's one in the second quadrant by looking at this graph. So for second quadrant angle, x will be 180 minus that 41.8 and so on. Now if I take that calculator, I've still got that value in it, so I'll get a more accurate version. So there's 180 minus this first quadrant angle, that gives me 138.2. And that's me rounding it again to 1 decimal place. So that's one way of finding the two answers that are required as solutions to this trig equation. However, there is another method that you might well have been taught, and that's to do with this quad diagram, where we have first quadrant, second quadrant, third quadrant and fourth quadrant, and there is a connection. You'll probably have been told C, A, S, T and so on, and in here it's 180 minus, and here it's 180 plus, and in here it's 360 minus. Now you can maybe get a hint that there's a connection here because we had 180 minus in the symmetry of this diagram for this second angle whose sine was 2/3. So there is a very profound connection between this, what's called the quadrant diagram, and the graph of sine. And we're going to explore that now. This is a little bit of extra to this question. So here we have this quadrant diagram of just the x and y axes and the origin, and we have a circle. It's called the unit circle. It has radius 1, and starting at the origin going out to this point 1, 0, we have a rotating line, and you can see that here. It starts rotating. Now we've highlighted the height that this end point has, and at present it's 0.5, and this angle is 30 degrees. Now in the normal sine graph, you read off 30 degrees, you go to the height of the graph, and you get the value of the sine of 30, which is 0.5. So in this quadrant diagram, the height of this rotating line, the height of the end of it, will read off the sine value. So we can keep going with this, and there's our value of 2/3, and this must be 42 degrees. We keep going, and eventually the arm has rotated by a full 90 degrees, and the height is now 1. And there's the beginning of the sine curve, showing you the values of the sine of the angles up to 90 degrees. Now beyond 90 degrees, as this arm continues to rotate, you can see the height decreasing again, and it's completely symmetrical with what happened from going from 0 to 90, and it's now going back down from 90 back to 0. And that's why we're getting a symmetry in this graph. And continuing into the third quadrant, there's the first quadrant, 0 to 90, second 90 to 180. This arm has now rotated beyond 180 degrees, and you can see the height, the y coordinate of the end of that rotating arm is now negative. And that y coordinate of the end, yellow end point of that rotating line is now -1. and the angle it's rotated is 270. And you can see in this graph we've now reached an angle of 270, and it's shown the sine of 270 as being the value -1. And we continue on into the fourth quadrant, angles beyond 270 reaching up to 360, and the values of the sine go back up to 0. And there we have a complete cycle of the sine curve. This arm has rotated a full 360 degrees, and we've marked out a graph showing the values from 0 up to 360, the values of the sine, and that's just the height of the end of this rotating arm. So that's the connection between the quadrant diagram and the sine graph. Now if we go back, remember we were looking for an angle that was 2/3, sine of an angle is 2/3, which is 0.666 and so on. So there it is, accurate to 3 figures. And remember we found out this was roughly 42 degrees. So the sine being 42 degrees in this first quadrant, but there is another position across here where we will get an angle where the height of the end of this rotating arm is also 0.669, and that is there. So this is the same height. Now where is this 42 degrees? Well, it's tucked in there. In other words, that arm has another 42 degrees to keep going till it reaches 180. Or if you reverse the rotation by 42 degrees from 180, you'll get to 0.669. That's 2/3 for the sine value. So this is where your 180 minus measurement is coming in. If we get the first quadrant angle being 42 degrees, that's there. Then the second quadrant angle, 180 minus 42, will also have the same value for sine. So here's this quadrant diagram again, and the significance of the A, S, T and C is that all three sine, cosine, tangent will be positive in this quadrant for angles between 0 and 90. Only the sine is positive in the second quadrant. In other words, the sine of angles between 90 and 180 are positive. You can see in this diagram the sine graph is above the x-axis. It's positive values we get. In here the sine is negative, in here the sine is also negative. Only the tangent has positive values for angles in the third quadrant, and only the cosine is positive for angles in the fourth quadrant between 270 and 360. So this CAST business allows you to determine where the second angle, when we solve sine x is positive, we know that's in the first quadrant and the second quadrant. So once we've got the first quadrant angle, we know to get the second quadrant angle we take 180 degrees minus that first quadrant angle, and that gives us 138.2 degrees. So that's the other way you might have been taught this, but it's nice to tie up the two diagrams together. You get a better understanding of what's going on, I hope, anyway. So this is question 10. We've got a theme park attraction where there's a carriage attached to an arm and it swings. Here's a diagram of it. It swings in the shape of an arc of a circle. And we're told that the length of the arm is 15 metres. The length of major arc AB is 69.4 metres. We're asked to calculate the size of the reflex angle ACB. Now you may not be sure about these words major arc and reflex angle, so let's talk about that in a bit more detail first. So here we have an angle at the centre standing on arc AB, an angle of 14 degrees standing on arc AB. And we can increase that angle. And there's now an angle of 90 degrees at the centre standing on arc AB. And you notice arc AB is 1/4 of the whole circumference, and this angle at the centre, 90 degrees, is 1/4 of 360 degrees. Let's move the angle on. And then we reach 180 degrees. So we have a straight angle at the centre, an angle of 180 degrees, and it's standing on, well, this arc is half of the circumference. It's a semicircle. So the angle at the centre standing on the semicircle is 180 degrees. And there's no reason why we shouldn't continue increasing that angle. And what we now have is an angle of 209 degrees at the centre, but it's standing on what's called a major arc AB. That's more than the semicircle, just as this angle at the centre is more than 180 degrees. And you'll notice there is a minor arc AB and an angle on the opposite side of this 209 degree angle, which is less than 180 degree. But what we're looking at just now is an angle at the centre that is reflex. It's more than 180 degrees, and the arc is what's called a major arc AB, which is more than a semicircle, and this continues. And we can go right on until we do get 360 degrees being the angle at the centre standing on the whole circumference. So this 360 degree angle, which isn't actually marked here because of this demonstration doesn't do that, but that angle at the centre of 360 degrees goes with the whole circumference of this circle. And we have, remember when we had the 90 degrees, we have the case that it's a direct proportion. So for instance, when we were sitting at, say, 25 degrees there, it's too sensitive, this, there it is, 25 degrees, the length of this minor arc AB, minor because it's not a major one, if we double that angle at the centre to 50 degrees, then that arc length also will double. They're in direct proportion. So there's a 50 degree angle at the centre, and that arc is now double the arc that we had when we had a 25 degree angle at the centre. And certainly when I stopped at 90 degrees previously, you can see that if I double that 90 degrees to get the 180, then instead of 1/4 of the circumference, we will have a semicircle. That's half of the circumference. So we double this angle at the centre, we will double the arc length. So there's the 180. If I can get that right. There's the 180. So that was double the arc that we had for the 90 degree angle, double the arc length. So it's in direct proportion. The angle at the centre and the length of the arc are in direct proportion. So armed with that knowledge, let's return to the question. And one of the things we can calculate here is the circumference of this circle. Remember, the circumference of a circle is pi times the diameter. Now in this case, we know the radius is 15, the diameter right across the circle will be 30 metres. That's double that. So pi times 30. Now we won't, let's just write it as 30 pi. We won't calculate that just now. We've got calculator handy. We can easily calculate that shortly. But it's 30 times pi metres. So that's the whole circumference. Now we're asked to find the size of an angle. So let's do two columns. Let's do arc and let's do angle at the centre. So what do we know so far? Well, we know that when we've got the full circle, that's an arc, it goes with 360 degrees, its length is 30 times pi, which goes with 360 degrees at the centre. And remember we said these things are in direct proportion. So if we half the arc, we'll half the angle at the centre. If we quarter the arc, we'll quarter the angle at the centre, and so on. Now, we're told that this major arc is 69.4 metres. So we're going to have a 69.4 metres in there, and we're going to have to work out the angle at the centre that corresponds to that. So let's do it in two stages. Let's assume we're after an arc of 1 metre. Now, had it been a 2 metre arc, to get a 1 metre arc we would have divided by 2. If it's a 15 metre arc, we would divide by 15 to get this 1. It's a 30 times pi, so to get 1 we divide this by 30 times pi, which means we do the same to the 360 degrees. So 360 gets divided by 30 times pi. And that'll give us the angle at the centre, it's in degrees, that goes with an arc length of 1 metre. Now it's not 1 metre we're after, it's 69.4 metres. If we had wanted the angle at the centre that now goes with a 2 metre arc, we'd double this. 3 metre arc would multiply it by 3. It's a 69.4 metre arc, we'll multiply this by 69.4. So this also, since it's in direct proportion, gets multiplied by 69.4. So wherever the degree, number of degrees, angle at the centre that goes with a 1 metre arc, the one that goes with a 69.4 metre arc will be 69.4 times that. And that's our answer. Now it doesn't look very healthy because we haven't simplified it. We need now to get our calculator out. So let's do that now. Here we go. And this is the calculation that we have to do. So let's do our 360. We could divide that by 30 times pi, divide by. Now I'm going to be careful here and put the 30 times pi in brackets. There's the pi button. So it's 360 divided by the whole of 30 times pi and then multiply by 69.4. So multiplied by 69.4. That comes to 265.08 and so on. So let's put that down. That equals 265.088 and so it goes on. It's that number of degrees. So let's just look finally at the question. Calculate the size of the reflex angle ACB. That's what we've now found. So reflex angle ACB is approximately equal to, let's take it to the nearest degree, 265. We're chopping a 0 off so we don't need to round it up. 265 degrees. That's the size of this reflex angle ACB, the angle that's bigger than 180 and it stands in this major arc AB, which is length 69.4. So here's question 11. We're shown a diagram of a cuboid, A, B, C, D, E, F, G, H. And we're given the 3 dimensions of the cuboid, 24 by 6 by 8. And we're asked to calculate the length of the space diagonal EC. So let's first of all get a feel for the 3-dimensional nature of this solid. So here we have the cuboid. Let's move this cuboid around so that you can get a feel for it. So a space diagonal going from one vertex to the opposite vertex through the middle of the cuboid. Now, to help us solve this problem, we're going to be using this crucial line along the base of the cuboid. Let's move that around so we can see what we've done. And should be looking for right-angled triangles, because of course once you have a right-angled triangle, Pythagoras' theorem comes into use. So let's just highlight the triangles that we're going to use. There's one on the base. There it is. Let's just look down on that. You can see there's the right angle triangle. So that's the right angle triangle on the base, and we're going to be using that triangle. And of course there's another one that we'll be using, which consists of this side, and the space diagonal. Let's move around to see that one. If we move to this angle, we can see that triangle better. Right angle triangle sitting in the middle of that cuboid. So now let's go back, and with these pictures in our head we can maybe make some sense of how to solve this problem. So here's the question again in the diagram. Let's look at this magic line EG that we highlighted a minute ago. So this is the crucial line to draw, because it allows us first of all to start work on triangle EHG. That's the base triangle there. So let's just have a look at that triangle. There's E, H, G, and that's a right angle. And we can use Pythagoras in this triangle because we're told a couple of lengths. That's the smaller sides, 24 and 6. So EG squared will be 24 squared plus 6 squared. And get the calculator out to quickly tell us the answer to that. And there it is, 612. So let's put that down. So that's 612. Now interestingly, we don't need to work out the square root of 612 to find the length of EG, and you'll see why in a minute. Let's move on now to triangle EGC. So there's EGC. And again, that's a right angle triangle. Now, this time we know the length of EG. Well, its square is 612. So it would be the square root of 612. Come back to that in a minute. GC, we're told, is 8 centimetres. That's the third dimension. The dimensions are 24 by 6 by 8. So this is the dimension we haven't used yet, 8. So again, Pythagoras' theorem in this triangle in particular, EC squared would be EG squared, and that's 612. That's EG squared, plus, and that's why we didn't need to work out the square root of 612, because we're just going to square it again. Plus 8 squared. And 8 squared is 64, so this is 676. So we're asked to calculate the length, so that would mean that EC would be the square root of 676. And let's get an approximation for that. So square root, let's clear that. Square root, where are we? There it is. Square root of 676. And that comes to exactly 26. So to answer the question, calculate the length of EC, the space diagonal of the cuboid. It's 26 measurements, centimetres. Units are centimetres. So here we have a algebraic fraction to simplify in question 12. Now, simplifying fractions, suppose we have 66 over 55. What you usually do is cancel out a common factor. For instance, in the top line here, we have 6 times 11, and in the bottom line, we have 5 times 11. Numerator 6 times 11, denominator is 5 times 11. And we can divide the top and the bottom by that common factor of 11. In other words, cancel these and we get 6 over 5 as a simplified version of that fraction. Now we do exactly the same for algebraic fractions. We look for factors in the numerator, top expression, and factors in the bottom expression, the denominator. And in the top expression, we'll notice that there's a common factor of 2, and of course 2 goes into 6. Also a there's a factor of, and a there's a factor. It looks like 2a is a factor in both of these expressions. We've got 2a times b, and then we can write 6a as 2a times 3. 3 lots of 2a is 6a. So there is a common factor of 2a in both of these expressions. So we can take that outside brackets. We're left with a b plus a 3. Now just check, if you were to multiply this out, 2a times b gives you 2ab. 2a times the 3 gives you 6a. So we've succeeded in factorising the top line. Bottom line, there's a square, b squared, and here's a square, 3 squared. And the difference of squares pattern, you can factorise that by writing, in this case, b minus 3, and then changing the sign b plus 3. Always check that that works. And you've got 2 brackets multiplied by this. You might know this as a firsts, outsides, insides, lasts. The first 2 terms, b times b, gives you that b squared. The outside 2 terms, plus 3b, and the inside 2 terms, negative 3b, they cancel each other. 3b minus 3b, they disappear. So there's no term here with a b in it. And the last 2 multiplied, negative 3 times 3 gives you negative 3 squared, that's negative 9. So this is what we call a difference of squares, so it factors into b minus 3 times b plus 3. Now we've a situation here similar to this 66 over 55, where we have 6 times a factor over 5 times the same factor, and that factor can be cancelled out. Here we've got a factor of b plus 3, something times b plus 3, and something times b plus 3 in the bottom of the fraction. So this b plus 3 can be cancelled out. We're really dividing the top and the bottom expressions by b plus 3. So we're left with what? We're left with 2a over b minus 3 as the simplified version of that fraction. Question 13. A trig question. Simplify this fraction. Well, on the numerator, the top of the fraction, we've got a sum of two trig expressions. And then on the bottom of the fraction, the denominator, we've got cosine of x. Let's look at a numerical example. Suppose we have let's take 2 plus 4 and we're dividing that by 2. Now you know that comes to 6 over 2, which is 3. That's no problem. However, there's another way of calculating this. Because we're dividing a sum by 2, we could divide each term of that sum by 2. So we can divide this 2 by 2 plus and divide this 4 by 2. We can split this fraction. That's what it's sometimes called, splitting the fraction. Let's check that. 2 into 2 goes 1. And 2 into 4 goes 2. And again, we get 3. It's a valid numerical process. Now, these are just numbers. They're just fancy numbers, decimal numbers in a lot of cases, depending on what the angle is. But it doesn't matter because they behave like normal numbers, and we can split this fraction. So our first move would be to divide each of the terms in this sum by cos x, cosine of x. So there we go. Now you might not think this is progress. It looks slightly more complicated, but it is progress. Now sine x over cos x is an interesting one. Suppose we have a right angle triangle, and this is x, and the hypotenuse is 1. The sine of x, you should know the SQA, sine of x is opposite over hypotenuse. Now that means that this side will actually be sine x, sine of x, opposite over hypotenuse. Sine x over 1, so divide something by 1, you just get this, sine x. And cosine of x is adjacent over hypotenuse. This is cos x. Cosine of x adjacent over hypotenuse, cos x divided by 1, which is just the same as cos x. And look at the tan of x. Remember, tan x is opposite over adjacent. Opposite over adjacent. Tan of x, tangent of x, sine x over cos x, opposite over adjacent, sine x over cos x. So we can simplify sine x over cos x to get tan x. Now, don't worry if you didn't understand this little diagram. You just end up remembering that sine x over cos x is equal to tan x. And let's look at the second fraction. We had numbers again, 2 times 7 over 7, for instance. You divide the top and bottom of this by 7. And that factor cancels. And you'd be left with 2 over 1, or just 2. And you know that 2 sevens are 14. 14 divided by 7 does give you 2. We're cancelling a factor that appears on the top and the bottom of that fraction. And this is the same. We divide the top and the bottom by the number that's cosine of x. That goes. That goes. And what we're left with? 2 times 1 over 1. That's 2 over 1. That's just 2. So the whole thing simplifies, and we're asked to simplify it, to tan x plus 2. So here we have the last question in the paper, question 14. And we've got a river that's represented by BC. And we're standing on the river bank here, looking at the top of a tree on the opposite side of the river bank. And we're measuring this angle of elevation, which turns out to be 28 degrees. Now that's the angle between the horizontal, as we look across the river, the angle you have to raise your line of sight until you see the top of the tree. That's an angle of elevation of 28 degrees. Then moving back 15 metres, we do the same from a different point, D, and we measure the angle of elevation of the top of the tree to be 12 degrees. And from all this wonderful experimentation and taking readings and so on, we're able, using the magic of maths, to find the width of the river without travelling over the river. So how do we do that? We have to calculate BC, the width of the river. So, fairly complicated diagram, but nestling in amongst all these lines are two right-angled triangles. Let's look at the small one. There it is. And since we're asked to find the width of the river, I'm going to call that x. And there's another right-angled triangle in there, much larger one. And there it is. And again, I'm going to write an x in there because that's the width that we're trying to find. Now, in this right-angled triangle, the tree and the river are on the opposite and adjacent sides compared to this angle of 28 degrees. And if we go down to this triangle, the tree and the other things that we're concerned about, the x and the 15, they're in the opposite and adjacent sides of this angle 12. And opposite and adjacent involves the tangent, TOA, SOHCAHTOA. Tan is the opposite over the adjacent. So I'm going to write that down here by saying that the tangent of 28 degrees, that's in the first triangle, is the length of the tree, and it's not exactly mathematical, but let's just write down tree as the length of the tree. Maybe put wee quotes around it, unconventional use. Tree over x. And in this triangle, let's look at tan 12, and again that's the length of the tree, or the height of the tree, over, now this time's interesting because x goes from B to C, and then there's a further 15. That's a sum of two distances. We've got an x plus a 15. But there is this tree, height of the tree, common to both of these expressions. Let's take the first one and get the height of the tree on its own. We'd do that by getting rid of this divide by x from both sides of the equation. We'd multiply both sides by x. So on the left-hand side, we'll get x times tan 28. And the x, of course, here would disappear, and we'd be left with the height of the tree. And let's do the same down in this equation, where we want to get the height of the tree on its own. We'd multiply both sides by x plus 15. So we'll get the number tan 12, whatever that is, times x plus 15, and then on the right hand side, that x plus 15 would just vanish and would be left with the height of the tree. Now you can see where this is going, I hope, because if both this expression and this expression are equal to the height of the tree. These two expressions are the same. So let's write that down. We'll get x tan 28 degrees, x times tan 28 degrees, has to be equal to tan 12 degrees times x plus 15. These two expressions represent the same thing. That's the height of the tree. And the height of the tree's vanished there, and we're just left with numbers like the tan 28, the tan 12, this 15, and the thing we're trying to find, which is x. So let's multiply out this right hand side. So left hand side will leave as it is, and each of these terms in the brackets gets multiplied by tan 12 degrees. So tan 12 times that x, put the x in the front there, x times tan 12, plus, and then tan 12 times the 15, 15 times tan 12. And let's try and get these x's together. So we're going to subtract x times tan 12 from both sides. So the left hand side will have x tan 28, x times tan 28 minus x times tan 12. And that's going to be equal to, we've got rid of that x times tan 12, we'll have a 15 times tan 12. And the final move here, before we make sense of this, well, I'm running out of space, I'm going to move it up here. There's a common factor of x in both of these expressions on the left hand side, so I can take that outside brackets, and I'll be left with tan 28 minus tan 12. Now just have a wee look at what we've written there, and let's do the backward step. Let's multiply out. So it'll be x times tan 28 minus x times tan 12, which is what we're sitting looking at there. So that's okay. We've taken out a common factor outside the brackets. And on the right hand side we've got 15 times tan 12. Well, this is progress, because remember we're trying to get x on its own to find what x is. If with a calculator we know all these other numbers, we can do a big calculation. So one last step, then we have to get rid of this tan 28 minus tan 12, and that's just a number. So we've got x times this number equals this other number, so we divide both sides by this number tan 28 minus tan 12. So if we divide the left hand side by this number, that'll disappear and we'll be left with x. And if we divide the right hand side by tan 28 minus tan 12, that's what we get. Now, our work is done. This right hand side just needs a calculator to sort it out, and we will have found what x is. So let's call upon the calculator to see if we can finally get an answer to this. Now, one thing to note at this stage, on my calculator this says deg. Somewhere in your display it'll tell you the mode it's in. It knows I'm going to be working with degrees, not GRD or GRA or RAD or whatever. There's all sorts of different modes, but it's expecting degrees. That's important when we use trig functions like sine, cos, tan. It has to know what we're measuring the angle in, and it is degrees. So make sure your calculator's in degree mode, and let's get going with this. So we've got 15 times tan 12 times tan 12 degrees, and then have to divide that. Now here's a problem. It's not just divided by this, it's divided by the whole of the expression tan 28 minus tan 12. To be safe, I'll put all of that in brackets so that I know it's going to calculate whatever tan 28 minus tan 12 is. Okay, an awful lot of brackets there, but all I've done is 15 times tan 12 divided by the whole of tan 28 minus tan 12. Your calculator probably doesn't have extra brackets around the angles, mine does. So if I press the button, there's the answer. So it's 9.990, and it goes on and on. Calculate BC, the width of the river. Let's approximate that. So x is equal to, and let's round it, 10.0. And that's to 3 significant figures, 1, 2, 3. And it's measured in meters. Or it's the 1 decimal place. So we'll say it's the 1 decimal place, it's 10 meters. That's the width of the river. Well, that's Mr. Corsi signing out, and hope you enjoyed the video.